Ah, I believe I'm live. Make sure it works. So wait a second or two, and then we can begin. Part of the necessary procedure, unfortunately. Unfortunately, it's not working. There it goes. Good. All right. Let's see if the sound works. Yep. Okay. So I believe we're in business then. So if somebody would, oh, well, no point in saying it now. There's no one will hear this part probably, and I should type it somewhere. Well, if you want an invite to the room, just ask, and you shall be invited. Um, Probably, maybe, depending on who you are. Anyway, I believe I've got the camera resolution a little bit better, so that's totally irrelevant and meaningless. But it's one of those things you have to consider. Kind of medium that way and such. So anyway, I figure we'll do a little talking about. I've just been looking at a lot of different things, and the Huygens thing, but it's just got me thinking about how to make this argument that there's lots of ways you can explain mechanically functions, and it's just the fact that they always reach for this stupid wave thing. All right, so some guy left a kind of a raggy comment. On the message board on the whatever website it is, the InMindyCam thing, and posting the Wikipedia page. Like these pages are horrible. The Wikipedia pages are absolutely horrible on all these subjects. But anyway, like I needed some sort of instruction on the history, and it's just kind of annoying. It says here, the wave theory of light wasn't accepted. Whoops, I should have turned off the refresh. It doesn't turn off. Yeah, well, I guess I have to fix that. Huh. Not turning off. Anyway, now stuff is broken. No, well, now it turned off. Anyway, I don't like delayed things. The wave theory of light wasn't accepted because of Huygens or Young's interference experiment, and so I'm not the one arguing it. Okay, so I'm pointing out what the professors at MIT say. So I'll play them saying it. Okay, so argue with them, you shithead. I don't need this crap, you fucking cunts. I'm just so sick of these assholes. I mean, you can't tell that I'm not the one telling the history. I didn't write the history. I didn't make up the history. I'm saying what they're arguing, okay? And they're arguing that Young is this big, huge, important experiment. And they all say it. I didn't make that up. They're saying it at lectures, at Yale and at Stanford and at MIT. Fuckhead. And then just about every science documentary ever made. So, don't tell me I need to learn. Tell them they need to learn. Fucking jackass. I mean, it'd be one thing if he posted a link to the Wikipedia page, but he had to post the entire text of the crappy page. And like I said, these pages are written by assholes, clearly. I mean, Wikipedia is disgracefully terrible at science. I mean, the Huygens page is idiotic. I mean, the guy who posted the paragraph in the comments, I mean, it's just an example. It's incomprehensible drool. Anyway, all right, so maybe we'll just get to some of that. Maybe I'll just play a little bit of this Walter Lewin stuff and, make my point. State my point. I think this is the video. So let me put the screen capture on. Hopefully that'll work. And we'll see how it goes. It should be this one here. Screen share. All right, so it should work.
The controversy between Newton and Huygens about the nature of light was settled in 1801 when Young demonstrated convincingly that light shows all the characteristics of waves.
Okay, it doesn't show all the characteristics of waves. So anyway, so you just heard him. He said it was settled, and then he says later, well, in the 19th century it was restarted again, but it doesn't even cite the reason why it was restarted, which was Einstein's basically pointing out that the conservation of energy argument, that the photons are obviously hitting the metal as discrete packets of energy. They're not waves, they're clumps, as Feynman would put it. And again, I can quote Feynman, who said they're clumps, they're not waves, but who cares? Just do the math. So yes, Feynman said, Feynman said it explicitly. And then, he's, at one point in one of his lectures, he says, look, just cut through all the bullshit. Photons travel from point A to point B in a straight line. And it's when they hit electrons that something happens. And he basically said that. And he just said, okay, the math says something different. Who cares? And he didn't care. But to me, that's an important thing to recognize, okay? It's if you have something, this whole duality thing, I don't think Feynman was at all comfortable. He says things like, all right, you can't understand it, and I don't like it, or we don't like it, or something. They said then he retracts his statement saying, it's not that I don't like it, it's just that, okay, I like it, it's okay, blah, blah, blah. But yeah, the fact was he didn't like it. He didn't like duality. Duality isn't a good answer. It's a stupid answer. But his response is, I'm not smart enough to fix it. Einstein wasn't smart enough to fix it, so fuck it. It's not going to get fixed because we're really smart, therefore it can't be fixed. So fuck you, you're stuck with it. And that was lame on him. So I'll play the rest of this.
Now, in the early 20th century, the particle character of light surfaced again.
Einstein. Okay, that's Einstein's Nobel Prize.
And this mysterious and very fascinating duality of being waves and particles at the same time is now beautifully merged in quantum mechanics.
Okay, so beautifully merged. No, it's not at all beautiful. It's ugly as fuck. It's a silly, stupid thing, creating waves that don't spread, creating waves that don't have any kind of dispersion. I mean, it's all stupid. It's just particles with radar. That's a beautiful solution. Particles with radar. That's what physics are. Physicists are going to make up extrasensory perception, ESP, and give it to fucking photons. And they're happy with that. It's a fucking religious solution. It's a God of the gaps solution. It smells, it reeks, it sucks. It shouldn't be what they settled for. All right. Later he brings up Huygens and whatever, so I won't. But I'm going to try to make sure I just do clips that I know what's going to be said, and we get to the clip. We do have the two. This copy seems like a much better copy of the two slit. So he does it. There's two lectures, and he has exactly the same thing. So 102X must be a copy of 102. A second version of it done another year, I guess. And this is a much nicer visual of the single slit. Sorry, you couldn't see that part. Anyway, so of course what I've been thinking about, okay, which is related, but so that's, your brain goes to the related thing, is more about these free electrons. Nobody talks about the free electrons and what they're doing in the world. They have to do something. There's no quiet space in space, technically. There's no point in any place you could ever go where there's something other than a place that has some charge on it, in the sense that you can have a balanced charge, sort of, a place where there's no, where all the charges balance and the sample charge won't be influenced. But there's technically just no place that's without charge. There's like gravity, it's everywhere in some form, in some weak form, maybe, but it's there. And electrons are going to be motivated by it. And they don't like being motivated, which is another part of this I think is interesting. I don't think electrons like to hold velocity. They'll be pushed, but they don't want to maintain velocity. So I don't think electrons would freely travel, like from here, from the Earth to the moon or something. You couldn't shoot electrons and have them show up on the moon. They just don't want to do it. They're not, they don't like to hold the velocity. I think that's true. It makes them they're particles in the sense that they're a bullet made up of, atoms, but they're a hard bullet, like a bullet. But yeah, they don't like to hold a velocity, and that's why they always end up absorbing something and then re-emitting it. That's why they're always. That's why they just don't hold on to anything you shoot into them. And they end up emitting some sort of radiation in a new angle or in a new form. They'll convert blue light into red light, and they'll convert things into different things, but they just don't like holding acceleration unless you put them between two, unless you point them at a charge, and then like at a hunk of gravity, then they'll be forced to move, but otherwise they don't like moving. All right. It's not like it's not like just the inertia problem. I just mean they don't like to maintain a velocity. They just seem to go where the stream goes, but they don't go if there's no stream. Something like that. But these are a key thing, because when you think about electrons, you can sort of understand that you can't really suck them out of an environment. You can move them with charges. You can apply some kind of high charge that repels them. But in repelling them, you're really having a whole bunch of them in one place. So you're repelling them with the thing you're trying to expel them with. So obviously it's like trying to get rid of dog dew in the lawn by putting dog dew on the lawn and having the dog dew scare away the dog dew. So it's like you're always still stuck with dog dew because you need dog dew to get the dog dew to go away. But you can't suck them out of anything with like a vacuum or something. You can't pump them out of an environment, because unlike the rest of the pieces, they have this I like to be alone thing. They like protons, but they don't like the electrons surrounding the protons, which creates this dilemma of them being weakly attracted, because there's always a combination of force. All right, and so as the atoms get sucked out, as you pull stuff out, the only way you're pulling something out of like with a vacuum is you're grabbing something, and then all the forces that are tying other things to it, all the magnetic forces that are holding all these things together, you're basically pulling on a bunch of things magnetically held to each other, and you're pulling that way. So once you pull, the stuff that's got strong attractions to each other, once you pull those things out, the stuff that's left behind is the stuff that doesn't like each other. And obviously you can pull, the atoms are a lot easier to pull out than the electrons. So electrons are there's always a free electrons bouncing about. And they're going to align to those little neutral points. And those neutral points are created because the nucleus of an atom, because of the way the neutrons are working, it's holding protons closer than they would naturally be able to stay next to each other. And so it's creating a big charge. So it has a big charge of protons, and then the smaller charge of electrons around it, spaced. So anything in any one position has a, like say, a +5 charge and a -1 charge. And then when something's far away, all it's going to feel is the net balance of that, which is a +4 charge. And as it goes further away, it's weaker and weaker, of course, just like gravity. But the point is, from a distance, it's going to appear like a +4, and the electron is irrelevant. And as it gets closer and closer, then the electron gets relevant and becomes stronger when it's close. So that's this interesting thing where the free electrons they're attracted to the nucleuses of atoms. They're repelled by the electrons that are held in the atom, the bound electrons. And so they just kind of float around the atom. So we don't count them as part of the atom, but they're probably always there in some number. There's some number of electrons floating around every atom, not the atoms inside the material, but the atoms outside have all these free electrons that are just floating around saying, I want to get to those protons, but yeah, I can't get through the barrier of the electrons. And like I said, if you just you don't have to listen to me, just listen to Feynman if you trust the conventional physicists, in the sense that this is the key relationship, is photons and electrons. And here you have all these free electrons, especially around surfaces. Just, you can do this by deduction, and there would be lots of influences based on how they're going to travel. So when you have something like surface of glass, the key is understanding that the free electrons, it's almost like gravity. They're lined up with the surface in the sense that they're bound to the surface. So that's where they want to move, is down. And if something comes in at an angle, a photon, the conversion is going to be something other than the straight line, because the electron wants to go down and the photon's bringing momentum in a direction, so you're going to get something that's not the direction. All right, so this sort of gets to one of the Huygens elements that that's more interesting even than the stupid. I mean, the other purposes they describe for Huygens. What the hell happened to it? Yeah, it's funny that my link broke the Wikipedia page because it doesn't do spaces. Ah, interesting. Guess I'll have to fix that for links. Yeah, the old internet days, they didn't allow you to do those spaces and addresses. Anyway, all right, so I will screen share again, but I think I have to make this screen bigger, or you're not going to be able to see any of this. All right, that'll do. But this page is just horrible, awful, disgusting. Yeah, it's all those things. Yeah, I guess I have to figure out which page is my live room here. There it is. Okay, no comments. Good. So I think we're okay. All right, back to this Huygens picture, and then we'll screen share again. And yeah, that's it. All right, so so here's a picture of light diffraction. Now, of course, they've drawn it as a wave. It's not particles, so it's this boxy thing. I guess you might be able to see my mouse here. And and so they have these waves coming in, but that all that means really is there's particles traveling at a frequency, a distance between them, and they hit the surface. So my argument is that on this surface there's actually free electrons in the up and down orientation, in the sense they want to move straight down because of the orientation of the protons in the glass, and they that's the direction the free electrons want to move. And so when the light comes in, it hits one of the free electrons, and so you get a change proportional to the angle that the photon comes in. So what Huygens did is so Newton and Huygens had two different theories. So Newton's theory was that light, so he was almost thinking of light as being a more complex element than a true quanta. Like, he didn't understand dimensions, I guess, the 3 dimensions. I get, well, he understood that, but he didn't really see light as a one-dimensional particle. But so if you understand it as I'm saying, I mean, I think it's just kind of obvious that light is a one-dimensional thing. It only has mass in one dimension. It doesn't have perpendicular dimensions. It just has mass in one dimension, the dimension of its velocity at the speed of light, and that's it. So Newton kind of thought of it as being a more complex element, that it had momentum in all 3, a component in all 3, the x, the y, and the z dimension. For the purpose of this diagram, we're just dealing with 2 dimensions. So his argument is that light would move faster in glass, and that what was really happening is that it's the glass forced a speed up, an increase in the velocity of in the in the straight down dimension. So when a photon hit the glass, it would speed up in one dimension and still be going the same amount in the x direction. So it would go faster in the y direction and the same speed in the x direction, and that would end up giving you this bent shape if it was faster. And Huygens is doing exactly the opposite. So he's using these stupid waves, but this really isn't a good description of what Huygens actually claimed these waves to be, because Huygens didn't say they did this bulgy part. He was basically arguing that the waves only perturbate in one dimension forward. And obviously that would make sense, because that would clean up all the little edges you'd end up with. Even if you draw circles concentric to each other, you still have that little tiny defect in your wavefront. Well, anyway, so this drawing I don't think is how Huygens would have drawn it. But anyway, so by Huygens' theory, he's saying exactly the opposite. So that a photon that came in early, that hits because of this angle at this early location, and a photon that hits at this later location, that it takes longer, right? So this would be your perpendicular 90-degree angle, right here. And this would be the time difference between this photon hitting and this photon hitting. And so Huygens was saying no. So now the waves are created they're slower in glass, so they move slower. And so this, he needs it to go slower just because, whoa, camera failure. He needs it to go slower because he needs it to have plenty of time to bend it. It wouldn't be able to bend much if water wasn't much slower. So because light moves so fast, he needs something to create the bend, and the bend would be the slowness of the wave, so the one side is not bending too much. I mean, if it was moving the same speed, then it would just end up going still at the same angle. So to make the angle bend, he needs to make it go slower. So it's kind of funny that he got opposite theories, for inverted reasons, because they changed the speed, essentially, of a different dimension. Why is the camera still doing that? Stop it! Stupid piece of shit. I hate this mechanism. Sorry, I know this is irrelevant to you because we're screen sharing at the moment. But just, I can't get the stupid fucking camera to just stay in that one location. It would be just perfect location, but it won't stay in that location. Just keeps on. Oh, stop it! Fuck, I'm gonna beat the shit out of you, cunt. Just keep pushing, fucker. See what you get for your trouble. Bastard cameras. Yeah. Anyway, right. So that's enough of that. I guess that's all. I just really wanted to point out that that was kind of a curious thing. But neither one of them, both of them are playing with it as if it's well, Newton liked particle theory. See, they made up this. So they have these animations here, and this has nothing to do with any reality. So you see this little animation. I don't know if you can see that or not, but they have that stupid animation playing, and that doesn't have anything to do with anything real. I mean, it's just a simulation of what they would think, hopefully, could possibly happen in some weird world that has nothing to do with reality. Like says, diffraction of a plane wave at a slit whose width is several times the wavelength. That doesn't happen anywhere in the real world. It's just completely made up. I mean, I guess it's their presumption of what's happening with single slit diffraction, but I mean, it doesn't have anything to do with anything. There's no evidence that that's what's happening at all. All right, anyway, I don't want to. I mean, it would just get sillier and sillier as I made the slit smaller because I'd have to make the little Huygens dots smaller and smaller. But anyway, this doesn't have anything to do with reality. So I don't think there's anything else in here that's terribly relevant. Just here's the quote the other guy quoted. It's just the most incomprehensible mush ever written. So anyway. Enough of that. So turn that off. And back to me again. Some new position because this camera's a pain in the ass. Anyway. So yeah, I don't know. I want to do something on that to play this two slit video, but I just don't know if I want to do it now. Yeah, so that's all I've been thinking about is it answers the question is all I'm saying. I mean, if you just take the free electron argument again, it'll answer the question of why surfaces are so frickin' important in these diffractions and refractions that take place when you transition between mediums. Because when you're transitioning between mediums, what you're really doing is interacting with a field of free electrons. All right, focus. All right, that's what's really taking place. So whenever there's a material that's different than another material, there's free electrons between the two materials, always. And it really doesn't matter how little material you have. There's also this idea of charge. So another thing I was thinking about was I was playing with a mirror, and so I want to do some more experiments with this. I think I'll use black tape, but what I just used was magic marker. And you can see the little slits on there, and it was kind of interesting. I think that's all you can see. It's nothing, no nudie pictures. It's kind of interesting, that you still get the interference pattern with a mirror, except it looks like you get it with just one surface. So you can get an interference pattern off of one surface quite easily if you use a mirror, and it goes in one direction. So you get the regular pattern, except it's only half the pattern. which is interesting. But like I said, I have to do some better experiments with, because my hands jiggle too much with my age. I'm getting a little Parkinson's, so I'm a little, unfortunately, a little jittery. Um, so when I do things with, handheld, it's not a great idea. I have to buy myself a bunch of clamps or something. I can clamp things to things. But anyway, so what's the point I wanted to make? Yeah, because I was just thinking of the fact that that's such a thin amount of material, tiny amount of just a little bit of carbon and ink, and yet it's diffracting the light. It's bending it. Something's bending the light. Okay, it's not the glass. It's the color. That substance is somehow changing the path of the light. And that's all there is. There's just a thin little coat of magic marker. Like the one problem with it is that it is thin coat of magic marker, so the laser light's a little too bright and it shoots through it a little bit, which is fucking the results up a little. So I'm gonna use black tape, and that'll create a nice little line. But anyway, it's curious, and I started playing with a magnet, and I'm just so sure somebody must have done this somewhere, but can't find anything on the internet easy enough. But I use two magnets, and then you can just bend them and create this crease kind of thing. And you put a little paper in there, and see that there's a little slit. You can see it there, right? A little slit. And I could not make a diffraction pattern out of that little slit. With them angled, there's no depth. They're just two corners meeting each other. And it was a little bit curious, though, that I got no diffraction pattern. But again, I might have just performed the experiment poorly. So I have to do some more research on that. And so the other thing I was thinking, though, is like these black surfaces absorb the light that doesn't go through the opening, right? So every time light hits a surface like that and it doesn't reflect off, it's clearly the energy has to go somewhere. So it has to be emitted as either heat, infrared. And so I was thinking, all these people with infrared cameras, maybe I'll ask the Ken guy. Well, I probably can't get my comments. Well, somebody else go ask the Ken guy, okay, because he has the infrared camera, to shine a laser beam at different surfaces and see if you can leave a heat signature with a laser light. That would be sort of interesting to know. I mean, I've never seen that done before. And especially thin things like slits or needles or something like that, just to see what kind of, if you don't have a heat signature, I guess the argument I would make is then you're creating EMF or something else. There has to be some other, like Einstein said, you're creating electricity when the photon comes in, hits the metal, and creates a movement in the electrons, which creates the magnetic movement, which creates electricity. And so if it's doing that, then that would also be affecting these electrons, the free electrons. If you're creating an EMF, the EMF would affect the free electrons, and that would change the pattern. Seems reasonable. If you change the charge, you'll change the association of the electrons. That's what I guess what I'm trying to say. Yeah. But again, it's the balance of the charges, so that's another tricky part of this whole thing. So, I mean, I think that's why the pattern in the two-slit experiment is a fusing of two patterns. It fuses. It doesn't just superimpose, but it fuses the single slit pattern and then the double slit pattern. Why did that jump in front of my screen? Very strange. I didn't ask for you. And so, because I have to do some thinking, I mean, if I can explain exactly, okay, how those two patterns get fused. I mean, how you have the the complete dark spots. The dark spots where there's no bands, little bands, and you have the big wave part from the two slit parts. So you have that. I have probably a picture here, but it's probably a mess. I've drawn over it. Well, people who know what I'm talking about will know what I'm talking about. But there is a true zeros, where in the two slit experiment you have a bunch of little bands and you have dead spots, really dead, no bands, no brights or darks. Both of them are annihilated. And then you have bright and dark, and then both are annihilated, and then you have bright dark. So it's and the total annihilation spots where there's no brights and a definite complete dark, it's a little tricky to explain how both of those patterns could line up to end up with that symmetry. It sort of argues against superposition, because in a way it would require the field energy to somehow have been converted into one thing. But that's sort of what I'm arguing, is that the electrons are doing that conversion. And so when you put an impediment in the double slit, when you create something in the middle, you change the field lines because you're changing the amount of charge. The charge that you would have, you could have, say if you had 1,000,000 volts across a surface and you put something in between it, well, now the 1,000,000 volts will spark between both of these gaps because the gap is too small. So this will facilitate the reduction of the charge. And so you'll end up with two 500-volt charges rather than one 1,000-volt charge if it was 1,000. Right. If you maintained a gap that was not going to destroy. So if you had a gap that had 1,000 volts over it and you put something between it, you'll end up with two charges that are 500 volts, I think. Yeah, I'm pretty sure. So much to keep track of. So anyway, so that's what's changing the compression of the field lines, which is changing how the electrons are moving. All right, and basically combining the two openings are tied to each other now through that middle impediment. The lines on one side have to match the lines on the other side. Yeah. My thing isn't working here. Better. That was good. Yeah. Anyway, so sorry, I'm tired. Yeah, every day is stuff. Cat's been waking me up way too early. So, taking all the fun out of this. So anyway, now where was I? I'll see if there's any comments. And yeah, so I think I covered what I wanted to cover. It's just the free electron thing has really got me thinking. There's nobody talks about free electrons, and they've got to be everywhere. I mean, just all over the place. Advocating Huygens. I still can't believe the author really said that shit. What the fuck am I looking for? Oh, okay, that's the page. 14 watching. Yeah, nobody's commenting. Huh. Strange. Somebody comment just so I can see if the comment thing's working. Well, I guess I could comment. I could just do one of these stupid faces. Do a stupid face. Let's see. Oh man, these are such stupid looking faces. I don't know why they did this. Why? Who wants to? They got 4 million stupid faces. I mean, what happened to the old ones? These are like for kindergarteners or something. Oh, just horrible. Yeah, I selected two of them. My mistake. All right, yeah, well, they worked. Yeah. Anyway, all right. Yeah, well, I'm not saying nobody's here. I just meant it was usually if there's questions or points people make, then I can respond to something and I can keep me going a little bit, and I don't have to generate all this stuff out of my own tired and beleaguered mind. Um, all right. I don't know if I said I didn't take notes or anything. It was just stuff that was coming to mind. I know I wrote down superposition because it's a concept used for a lot of they use the word as if it has a whole bunch of meanings, and what it really just means is that, like light bulbs, if I have like a red light and a blue light, the light doesn't mix until it hits something. They're independent forces. So like all these forces are independent forces. The forces themselves can't mix, and they're only mixed when you put something there, something like an electron, some material thing, something other than a quantum, something other than just force. So something more massive than force, if you put that there, then it will be affected by both the forces as if the forces were acting alone. And that's where you get this idea of your velocity when you're moving or being moved, that you have already a velocity and that the new force is just added, and what you're really doing is still doing the two forces in a way until they're combined into your new velocity. Um, let's see. So while you're accelerating, let's put it that way, the force is independent, and it's not until you've established it as a velocity is the force been combined into your new orientation. So it's like your gyroscope stays where it is, and it's just it moves. So it has an orientation, but it's not moving that orientation. That's probably not the right way to say it. Well, anyway, but it is a curious thing. And so, well, anyway, that got me thinking about the electrons, like I said, and the fact that I don't think electrons like to hold a velocity. So I have to make that clear. But that's this whole argument about the force they're admitting in acceleration versus their natural charge. And their charge only exists when it's provoked. So it's kind of like the gravity argument, that it needs to be induced. So in a sense, the electron has no natural charge. And that's why this gets confused with magnetism and electricity. Because magnetism is really when it's accelerating and it's giving off a field. And the native charge has more to do with the perpendicular. So when an electron's accelerated, okay, so you're moving it, it gives off a perpendicular. So this is when you're actually pushing, not when it has a velocity, but let's say when you're actually making it change. So when its inertia is changed, then it gives off this perpendicular EMF. The magnetic field. And when it's at its regular state, it doesn't have anything. But if it's the protons over here and electrons over here, what's going to happen is, okay, the electron's going to move towards the proton. It's going to do that by changing, not perpendicular, but forward and back. So it's the polarization of this is going to exchange. Okay, and that's all that ever happens. So you always have to remember there's always the same amount of junk everywhere, and all you're really changing is the polarization of the junk everywhere. So what this holds is polarization, that is stuff going this way, stuff going that way in terms of at a polarization, a color, is all that's going to change. So when it's moving, it's obviously absorbing the stuff it's made of. So this is made, the proton's red, the electron's blue. This is going to start absorbing blue to move. This, if it's going to move towards the electron, is going to absorb red to move. And that creates this imbalance between them in the sense that this has to release blue and this will be releasing red, so to speak. Yeah, because it has to do a conversion. It has to steal the blue from some other. It's like the blue will come in this way. It'll exchange the momentum going this way. It will release the blue that way, and it'll keep the blue going this way because that's the thing giving it acceleration, and it'll release the red. Yeah. But it's going to release the red forward, not perpendicularly. Okay. So if it releases blue perpendicularly, so the perpendicular would be it's the blue color, forward would be the red. Okay. Right. And the exact opposite for the proton. But the point is that the energy between them doesn't exist until they exist in a relationship. So it's not until they start moving, accelerating and accelerating, accelerating. With each acceleration, it feeds back into each other. So they're ending up creating more reason to accelerate. So the more they accelerate, the more they create reason to accelerate. So within a feedback loop. So their charge, so to speak, increases as they accelerate towards each other. So the electron has no charge and the proton has no charge until they're actually accelerating. And when they reach whatever their maximum acceleration is, that might be what we call their charge. No. I don't think so. Not sure on that. That one I have to think about. They are constantly vibrating, and that would be at a very high rate, so that does make sense. They could be vibrating essentially at the speed of light. They're being jostled by the field irregularities at a speed of light very, very fast. And so they'd be constantly releasing a little bit of this energy, and that little bit will become a lot of it as they start accelerating in one direction, and it gets stronger and stronger between them. Yeah. I think I like that okay. So when you measure something, though, you see that's another point. Sometimes you have to understand that the universe is functioning at this gigahertz kind of time scale, gigahertz squared, I don't know, whatever you want. It's very, very fast rate, very good frame rate. And we just end up averaging what's happening. So it's like if we see a stream of electrons or a stream of current or some other thing, we could say it's going 50 miles an hour. But the truth could be that some pieces are going the speed of light, some pieces are going really slow. It could be that we're just ending up averaging something that's a lot more irregular than what we can perceive with our instruments. that's just a general statement. I mean, I'm not applying that to any specific thing, but it's something you always have to be aware of when you're thinking about this stuff, is that we have equations and we have math that says certain things are in direct relationship to each other, but that relationship is probabilistic. It just means that over time, over a period of time that we can measure, or over the period of time, the thing that we can monitor, like we can almost monitor electrons in some sense. Yeah, well, there's could be a billion interactions happening inside an electron, and we're not monitoring those billions of interactions. We're just monitoring what's the overall effect over a period of time that we can measure. And so it's not a direct relationship. It's a direct relationship to a probabilistic outcome that some pieces might be 1% is going the speed of light and 1% is going the speed of a turtle, that kind of thing. And then 2% are doing this and 3% are doing that. And obviously most pieces are going 50 miles an hour, but there's a certain percentage that are going higher than 50 and a certain percentage that are going lower than 50. Yeah, something like that. All right, so I guess I could play the double slit thing. Yeah, well, I know I can. I don't know if it's if this is what I want to do at this moment or not, but it's what I think I will do. All right, so I'll go back a little bit. It's a little bit of annoying, this guy Lewin, but whatever. Everybody's a little bit annoying. So he starts off with it's a very nice laser image. I think I'll go big screen here so you can see this better. And screen share, and this one, and okay. All right, so we'll play this. So that's a laser going through about a 5mm opening. So it's just the laser.
And so the size of that slit that you see there, the size of the bright spot, is now entirely dictated by the divergence of my laser beam.
All right, so the divergence of the laser beam. So, it's hard to know what that exactly means, but you do get these radial things that happen, and I can't remember what they're called or why they exist. But it's there quite obviously. The video captured it. Now that might be a lens artifact. So in reality, that doesn't really exist. That little star shape is just a lens artifact because the aperture of the camera is causing that. But it does have this symmetry thing, and in the argument is that there's 3 lines, right? 1, 2, 3. Again, 3 showing up. And you can almost see that as almost the 3 dimensions again. But, let's not go too far.
The diffraction width is negligibly small because A is very large. Now what? Now I'm going to tighten, make A smaller. And I'm doing that now. I'm making it smaller and smaller. The diffraction which is still negligible. Making it smaller.
Well, diffraction width is not negligible. Now you quite obviously can see it spreading. So it's basically the same star kind of pattern. And what we're doing now is that we're creating another aperture. Okay, so there's the aperture of the camera looking at this. And this aperture now is the aperture that he's creating that only has 2 sides to it.
Smaller. I'm beginning to see the dark line.
Right, so now this is single slit, and again, whenever they draw it, I'll show you, like he has his own drawing on the blackboard, and they always show it the same way as, all they really give you is this central maxima and these 2 little humps next to it. So they just give you this big, huge thing, and then 1 little hump and a little hump, and that's it. but obviously it's a rich pattern at a wide opening. And there's no, it's not doing what the double slit does, which is that, it doesn't do the, so the point is the double slit is actually happening inside of this single slit pattern. So these, where the double slit breaks is the breaks in this. And you can sort of see this is, that this is just, as he makes the slit smaller, it's almost the same thing as putting the screen further away. So in a sense, he could just keep bringing the screen closer, okay, and maintain the same appearance, which would be an interesting experiment to do. As you make the slit smaller, just keep bringing the screen closer. And would you maintain exactly the same appearance of the pattern?
Fraction which is taking over.
Okay, so there it is. I'm really quite obvious now. So the secondary maximas were basically consumed in the central maxima. So that's why that was so bright originally. So if you look at that like a piece at a time, you can sort of see what happened there.
Making it smaller and smaller. The diffraction which is still negligible. Making it smaller. I'm beginning to see the dark lines.
So so he goes too fast right here. If he just turned his little dial a little bit slower, you could kind of see that the secondary maximas actually pop out of this primary maxima. So it's just that we can't see the lines because the light's just too bright, but they were there inside of that bright spot.
The diffraction which is taking.
See there, you can really see it. There's where they're first coming out, emerging.
Over. Look at the center maximum, right there. It's getting white.
All right, so it's funny that both of these lectures, he says it almost exactly the same thing, and it is kind of funny. I guess he did this stuff, these lectures were just a performance of a kind, but it's kind of funny because it's not exactly well scripted for something to repeat exactly.
It's getting wider, and I make the slit narrower. It's getting wider. It's getting wider. And look how beautiful you see these destructive.
Yeah, so again, these destructive, and then he's going to say the magic words, which are, see, the other part here, I don't know whether you can see that. I wish I had a pointer. But you really have to always keep considering that you have to go with the middle of the little light bumps to really appreciate that that's exactly the same distance, but they end up looking like they're further separated in different locations, but you have to go through the middle of them and then you figure out it's the same distance.
The interferences, where light plus light gives darkness.
It's the same line, light plus light gives darkness. Exactly what he said in the other video.
Wider. Wider. Right now it is at least 10 times wider than it was before. Now it is 20 times wider, and it gets very faint.
Right, so now it's almost...
It gets very faint, because if I make the slit very narrow, not much light goes through. There's nothing I can do about it. But notice how incredibly impressive this is.
Right, now if you brought the screen closer, you might be able to regain or recapture those pieces he's lost. So that would be the interesting part of the experiment, is if you change the focal length, will you get back what you're giving away by spreading the pattern?
How wide that center maximum becomes, that is very characteristic for diffraction. The narrower the slit, the wider. So
to begin this lecture, he said it shouldn't be called diffraction because it's an interference pattern. So, and then he just calls it diffraction, which is,
the diffraction pattern at the center maximum.
So
now, this is in
how he transitions.
Monochromatic light means that you have...
Okay, so you can see on the blackboard there, he's only drawn one side of it, but they have the big central maxima, and then you have the little tiny little humps. But I mean, obviously the pattern was much richer than what he drew here, and That's the truth.
Practically only one wavelength. And there is a way that I can make you see this from your own seats. And that is what we're going to do with the...
So I won't bother with that's diffraction gratings. So they're going to do white light for no real good reason because, you know, it doesn't make as nice a pattern. So why bother? But I guess it's good for, you know, teaching, you know, the fact that the different frequency light creates bands that are further apart or closer together, you know, blue being tighter, red being wider. And so I guess that's somewhat interesting, but not terribly interesting. And so anyway, enough of the screen share. Yeah, just stop it. That's what you do, Gary. Hit the stop button, and that'll stop it. Ah, very good. All right. Yeah, I'm just irritatingly tired. Yeah. So sometimes Australia guy shows up around 2, but I don't think I'm really gonna survive that long. All right, so my point is that this is about free electrons. The free electrons aren't as they've described them. They, you know, classical physics thinks of electrons as spinning around atoms, doing all of this velocity thing. And now they're like magnets, and they're in geometric locations, and they knock each other out of those locations. So say if you had a hexagon, and so the points are where the electrons are around a proton. So they can't collapse any further because of their own tension between each other. So their tension between each other, this one is like almost like the peak of a roof. So you can sort of understand that a triangle would be like the peak of a roof, and you can't push it down without pushing these out. So nothing can really go in because everything's the peak of some roof. Everything's the peak of a triangle and like a hexagon. So nothing can go in any further. They're bound to their own hatred for each other, even though they want to be pulled into the proton. And so they're not spinning. They're just locked in locations. And that's what makes the bonds between atoms so strong in some molecules, is because they are locked in a location. They're sharing a magnet, and you can't change the magnets. You can wiggle them, but to knock them loose, you have to replace them, or the number of them is reduced, and then you have a smaller orbit of electrons. So if you go from a hexagon to a square, okay, but that's really it's really geometry. I mean, atoms are geometry. You know, a lot of geometry. So yeah, I want to work on that. What was my point? Oh yeah, so the free electrons are also going to be affected by that geometry, and they're going to line up in a semi-rigid location of balance. They're going to find a balance in the force, and that's where they're going to stay. And when a photon hits them, they're going to move in a direction that has to do with what the forces allow them to do or oblige them to do. And that's when it's going to be the end of the superposition, so to speak. Superposition ends when the photon hits, because now the electron is going to convert it into a new position. Yeah. So the electron is going to travel the field lines, and in doing that, it's going to be like a parabola in a sense too. There's a good way to draw it. I should have got a piece of paper for this purpose. Well, we'll try the back of this paper and see how that works. And get me some nicotine. I just wish I was a little more low energy. Anyway. Okay, so how do I want to draw this? What was I going to draw? Field lines. All right, so if I have field, and field lines, let's just say these lines just represent the direction of the, I could say the electric field. Well, I won't bother saying that. So anyway, okay, so I'm just going to draw the complete thing, and you'll have to understand what I'm doing. Well, I'll point to it and try to get you to understand. Nothing travels the actual path of the line. It just travels the direction at any one point in the line. So it's a straight vector. And so it would want to go straight on that line. So if I gave an electron acceleration on a field, it would want to go one path, but it's going to end up, because it's going to get influenced by the field as it's moving, is going to move it, and then it's going to hit a new line, and then it's going to take a new vector from that line. So that's the nature of diffraction. All right, so gotta be able to see this. Wow, a little bit too bright, maybe not. Focus, hopefully. Yeah, well, that's too bad. Yeah, all right, that's not too bad. So the point would be is that if I hit this electron that was sitting here on this field line, it's not going to take this curved path, but it's going to take the straight vector from this location. And so it's going to go this way. But as it gets into this field line is being created by a field that's obviously, this is the balanced point in a sense. So now it's going to bend as it goes through the field. And so it's going to end up being a bent line eventually, because the field is going to bend it as it tries to escape. So it's going to end up being some kind of parabola as it goes through the field. But it's going to be one of specific angles, in the sense that the longer the parabola, let's see how to say that. Yeah. I'm just trying to think of how to point out these are. See, they say things like there's an infinite number of tons coming out, but there really isn't. So they say infinite, but there's obviously, it's like there's not an infinite number of photons coming out of a light bulb. There's a finite number, and they're diverging as they're going out, and that's what the field's doing. And those field lines just represent the same time location for the field. So everything at the same time location. Yeah. Because that's the divergence of the strength of the field. The field proportionally diverges, and that's the strength of the field, and a certain time is a certain distance from the location in blah, blah, blah. Okay. And then when you combine another field, you're basically just bending, another source of energy, force. Yeah, another source of force. All right, well, I don't want to complicate things. So anyway, my point is the electrons don't move straight. They move, not straight. And what they're really doing is changing positions with another electron. And when they do that, or when they settle into a location, is when they decelerate and release a photon. So that's why the photons are refracting, are diffracting. So the refraction into something and the diffraction past something, right? So that would be diffraction. And then the reflection, it's all the same thing. It's just photons hitting electrons, and the electron can't move in the same direction as the ton. So again, the reason why glass works with when you're looking straight down, so if you look straight down at glass, only a tiny amount of the light will get reflected because most of the electrons are oriented to go straight towards the glass. So they're all quite compliant with your request, in the sense that the photon will be transmitted accurately from one electron to the next because the electrons will move in straight lines. So if you're looking, so it's that orientation that's critical. And in those locations where the atoms of the glass, when they line up, there's specific locations where the atoms, because of the way the atoms are, there's going to be specific locations where there's a little bit more of the proton showing. So as the atoms on the surface of the glass line up, there's going to be locations that are a little bit electron heavy, and then locations that are a little proton heavy, and locations that are more electron heavy. It's not one perfect surface. And that is responsible for the reflection. The 4% of the light that reflects is a consequence of the fact that there's not a perfect symmetry in the surface because the atoms aren't perfectly symmetrical. It's like the hexagon thing again. If you have 5 sides, you can't line up 5 sides. They all have to have roofs pointing this way or this way or this way. You can't make a flat. You'd always have to have a flat surface with 2 down sides, and a flat surface is 2 down. They just can't be a perfectly flat surface. Let's see. So who's this jerk? I bet Inmendum isn't wearing pants. And that's important. How? Is that what you're here? Why you're here? In case he isn't? Yeah, it does seem like that's Jacob's fascination. I'm here to watch this Scandinavian Jew do his voodoo physics. I mean, this is just so bizarre. Scandinavian Jew. I guess I'm smart, so you just assume I'm Jewish, right? I guess that's it. That's funny. Well, he does have a harem. I think he's a polygamous Jew. Yeah, well. Doesn't matter. It's all a head game, fucker, and you don't got the head for it, quite obviously. So, good night, Jacob. Anyway. So, that was a useless commenter. Einstein would have got nowhere in the modern era, right? All these distractions, he would have never got any work done. But, as it turns out, he didn't get anywhere anyway. Got everything wrong, unfortunately. Whole big pile of it anyway. So it's these free electrons of the game. They're, and again, physics doesn't talk about it, right? You don't hear. I mean, they obviously keep ignoring physics in physics, right? I mean, the 2 slit and the single slit. Nobody will ever talk about surfaces, so they never call it the 4 surface experiment or the 2 surface experiment. They always call it the single slit or the double slit because they just don't care about surfaces. And they certainly don't care about the atmosphere that the light is traveling through or anything about it. And it's just really curious. And especially when you have experiments too that, I talked to it with the Australian guy, that if you shine, ultraviolet light through a spark gap, that you will increase the likelihood of a spark. You'll change the discharge. What do they call that? The stupid. Fuck. Hey. I hate my brain some days. I'm trying to think of the there's a word used. I think it has a K as a value. But anyway, it's the ability for charge to pass through a medium. And there's a word for it, and I just can't think of it. Well, anyway, it just increases the decreases the resistance. Well, it decreases the resistance to the electricity, and it's doing that because it's ionizing the atoms in the atmosphere. So again, we're back to these electrons. It's the release of electrons that are making it happen. The movement of electrons. And so, but yeah, physics just ignores all of these things. It ignores what Einstein got his Nobel Prize for, which is photons hit metal and are creating electricity. And it just seems like, well, why is it happening with a metal? Well, it's happening with a metal because there's free electrons. There's a lot of free electrons, more free electrons than in other substances in the metal itself. The metal has free electrons, but there's all these free electrons anyway. These static charges are on anything. I mean, nylon, rubber, every substance carries this capacity to carry a static charge. And all that is free electrons that have now been applied to a surface. There's a weak bonding possible. So if you push the item through electrons, you can collect the electrons. I mean, that's all that's really happening. You're just collecting them by applying them to the surface, by taking them from a place where there's a bunch of them and smearing them on like peanut butter or something. I mean, it's really almost that simple. That they're not bound strongly, and so if you apply them the right way, you can get a lot of them to stick. And if you apply them to something like glass, see, that's the trick with glass. I was pointing out the 5-sided. I have to go look at the chemistry of glass because it's likely got really very rigid geometry. But like I was stating, if it has a geometry, like I said, of this polygon thing, you could imagine that when it charges, what's happening is the charge is being held in these kinds of locations. And so the charge is kind of hard to get it off. So once you apply a charge to glass, it's kind of hard to get the charge off because you've put it inside of a bunch of little holes. And so now it's a little more difficult to get it to charge off. You actually have to create some other agent that'll bond to those. They're free, but they're now kind of a little bit bound and a little hard to pull off. And so, once you put a charge on glass, it just kind of sits there, and you really have to work to get it off. You have to create a lot of EMF, motion, to create enough magnetism to pull those electrons off of there. Yeah. So I think that's a good theory. Yeah, I think I got a lot of good theories. I think I got this thing nailed. I just gotta, if I can do like I said, if I can come up with a real diagram of how the two slit pattern, the superimposed two patterns, why they come out that way, like it's the middle parts creating one pattern and the exterior is creating the other, but the key ingredient is they're being balanced in the sense that they're being changed. It's really a single slit with changed field lines because of the single impediment in the middle. It's reduced the field strength between the objects. Yeah. And so the free electrons are in different locations. But it's all about the locations of those free electrons and their obligation to move in a particular direction. Yeah, so I just have to do a good drawing of that, and then I'll have it. I mean, that'll be that at least that could be one piece of evidence that would make me more credible. Yeah. All right, permeability is not a good word for me. But the idea of opaque and transparent, again, this goes back to this electron. The electrons have to be able to move in the sense that if you thought of them as magnets, so let me draw it more like a magnet, and they're in locations in the atoms, because of the way the atoms have like a rigid pattern, you can sort of understand that this would be the change in the speed of light. So let's say the electrons are, let's say there's atoms, so there's nucleuses over here and over here and over here in the glass. But what's really happening is it's always with this electron shit. And so what's really happening is that the photon comes in and it jiggles this electron, and that jiggles this electron, and then that jiggles this electron, and that jiggles this electron, because they're all held, they're bound together. And the net effect of the jiggling ends up being the straight line. It's just that now the straight line, the real distance is this, so that's how much slower the speed of light is this added distance. But the net effect is exactly the straight line. I mean, it still went, the force ends up going straight because the jiggles are always opposite, if you get me. And so that makes something transparent, and something can't be transparent if the geometry of the atom is such that there's an electron here, and then there's one here, and then there's one here, and then one over here. Then there won't be any proportionality, and the photon goes this way, or it goes over here. And so then it just ends up creating heat, or creating, infrared radiation is emitted, or it or it creates or it moves the electrons. Instead of jiggling them, it moves them. If it moves the electron, then it creates the EMF, which will be the photon leaving as a magnetic field. Yeah. So that would explain the Einstein thing. Yeah, so I have to, so that would also be good if I can get that geometry thing down, look up some chemistry, and, but yeah, I really do think they have it all wrong. I don't think electrons are spinning around atoms. Nope. So they can't measure an electron in any kind of pure environment. There's no way to put an electron in isolation and measure something about it. You just can't do it. It can't be done. You can't measure anything about it with any instrument because it's too small. I mean, it's so much bigger than a photon, but even an electron's too big to measure without influencing it with the very forces that will define its mass or its weight. So you just can't do it. Yeah. I mean, the only way you can know what it's made of is to accelerate it to the speed of light and then count how many photons are in it. So I guess they've done that in accelerators so they can get some idea of its mass that way, but that's about the only way to gain any information about its mass that's not going to be polluted. But it's semi-polluted because you're using a tremendous amount of force to move the electron. So, I don't know how accurate your answers are ever going to be. But I don't know every method they've tried to use it, to measure it indirectly. But I think everything just comes down to some sort of relative comparison. So, atomic weight is just, start with a hydrogen with a 1. But if you started with some other element as the 1, like a photon, that might be a better way to measure atomic weight, is to figure out how many photons are in an electron and find out how many photons are in a proton and a neutron. And they sort of do that when they do the nuclear thing, when they convert, when they do the alchemy thing of shooting neutrons into atoms and breaking them up. They call it electron volts, and they call it something else. And those terms almost end up being something very, I can't remember the word they use. Damn. But it's much more quantitatively connected to recognizing it almost as in a quanta scale, rather than any other scale. But that's the scale should have always been, but they got to fix the scale thing in physics because that's something so broken. They have way too many different scales. They measure things in pounds and ounces and this and that. None of them are, they need one quantity to measure energy in. All right, so I guess that's enough for tonight. I'm tired. Just wanted to do a room to stay, in the game here. Yeah, and I'm just saying I'm still doing research on the Huygens thing, and so I want to put all the little clips together, and it's just going to take time to do that, I guess, just to get this, just so people quit making arguments to me about what people are saying when I played the clips in isolation in different videos, so they're there. So I'm not making any assertions that I haven't already demonstrated to be true. And it's just irritating to have these people keep telling me that I'm saying something when I'm saying, no, this is what the professors are saying. I'm repeating what they're saying. I'm not asserting these things. They're asserting them. So it's not like I've misunderstood physics. No. If you have a complaint with the interpretation, take your complaint to the professors teaching it that way. And I don't think the complaints are relevant anyway. I mean, it gets down to semantics because the principles are wrong. There's nothing wave-like. Waves have rules. Waves travel in mediums. Waves are a vibration. That is, waves, generally speaking, are when something the thing itself doesn't go there, doesn't move. It's just moving the movement. So the idea of movement, this thing moves a little. The force in between them moves this one a little. And the force in between these moves this one a little. Then the force in between these moves this one a little. It's like dominoes. And the actual domino doesn't move. Just the falling moves. And so unless you're willing to create a universe of dominoes under tension, which is okay with me as long as you put them under tension, you can't talk about a wave. And even if you did, you wouldn't call it a wave anymore. You wouldn't say that if I knock over some dominoes, you don't say it's a wave of dominoes. It's a line of dominoes. The dominoes don't wave. They fall. Yeah. No, it's just the wrong way to describe it. They're things. The universe is made of things, and the things are in groups. So I'll just end up back at the school argument. It's like somebody shoots me in the head and my head turns this way. And as it turns this way, I have a gun pointed at somebody else's head, and my gun goes off, and then it shoots that guy in the head, and his head turns sideways, and his gun goes off. You know, we're not waving. I have to take it some other way. This is what makes, the only thing that makes water wave is its tension. All the atoms are tense. They're tied to each other tightly. Well, sort of tight. The molecules are bound. They're locked arms. And so, what happens? So, and then the ones that are going next to the surface. So when water goes through a slit, what's happening is the water on the sides is trying to grab the wall. Okay, so it's bound, it's holding its locked arms with the other guys, and then it's got a free arm, and it's just grabbing onto the wall. And so I'm slowing down, and so I'm turning, and everybody else is going fast still, and I'm slowing down, but I'm grabbing onto the wall. There's no parallel for that with light. I mean, first, the photon certainly doesn't need to be greased to get through something. It doesn't have any friction problem. It doesn't bond to anything. And then you're saying, okay, it's making a force in front of it, or a radar or something. And then you'd have to say the radar was somehow having friction. And somehow the radar was slowing down against the surfaces. I mean, it just doesn't make any sense. I mean, you just can't bulge the forces. This can't be done. There's just there's no locking mechanism. They've done the two-slit experiment with single photons. If you just can't make up this story that there's some stretching and it just is not happening. Yeah, reaction, counter reaction. It's the equal but opposite reaction is probably a better way to say that. But even that isn't really accurate. It's garbage in, garbage out. Let's see, how else can you say it? I mean, if you it's kind of funny because it's like I said, the momentum in the universe is always the same, and theoretically, and there's the same amount of polarization, and all you're really doing is changing what momentum has what polarization, but everything is moving exactly the same. The only thing that's changing is the relationship between the individual things, momentum, and its polarization. So it's like you either say everything keeps exactly the same momentum and it just changes color, or you say everything stays the same color and it changes momentum. But you can't, if you say both, then you're fucked. So you have to think of it as a universe where things interact, bang into each other, and change color, or you think of it as a universe where things interact and they change direction. But you can't do both. If you do both in the same, you'll break the rigidity of the universe. The universe really is rigid in the sense that there's always the same amount of stuff going this way as going that way. And the only thing that's changing is the color of the stuff. Yeah, that's probably a good enough way to say it. But anyway, okay, so that's probably enough. I don't know why that screen keeps popping up. Huh, strange. Doesn't really matter. So anyway, at least I think the video quality is a little better. A little too green still, I think. I don't know why it's green. Guess I could try some different lighting for that. Yeah, that doesn't really help the green any. Yeah. So, uh, yeah, I don't, the stupid camera preferences don't give you a color balance. You know, so you can't add some red, which it needs, I think, or it needs less blue, or it needs something. That doesn't matter. It's close enough. I guess I could try to fix that while I'm live in the room, which sounds really clever. All right. Let's see. Gmail. I'm not doing that. All right. Well, satisfied with the focus. I don't want you to follow my face because that will just confuse you. All right. So yeah, I got white balance. Yeah, color intensity. Really irritating that they don't give you. Yeah, I could do that. Ah, that might be a good look for me. All right, so I'll do that. Less brightness. And then I'll add contrast. And yeah, I just can't change the color though. See, white balance. Maybe I can do something with that. Nope. Can't really do anything with white balance. Yeah, it's just irritating. I think it would be much nicer if they gave me colors to play with. Yeah, really have to have the exposure up. Ooh, that's kind of an interesting look. All right, high exposure, high gain, and then we'll lower the brightness. Ooh, now we're getting interesting. All right, I'm liking that. And then we'll increase the contrast a little more. All right, I can live with that. Yeah, that's pretty good look for me. Yeah. Rawr. All right, maybe a little less color intensity. Let's see what I've got. Oh, yeah, that's kind of almost pleasant. Yeah. All right. So I shouldn't have played with this because then I just end up doing something stupid, like making it all much worse. Yeah, I sort of like that. But now it'd be great if I could just add some blue. Crap. Let me see if I hit the auto setting. See what it does. Auto. Ooh, okay, bingo. Yeah, that's pretty good. So now my eyes are blue. I like that. Yeah. Cool. Yeah. All right, we'll live with that for a little while. Maybe a little less gain. Maybe I'll bring in more contrast. Maybe I'll bring in a little more facial features. Nope. Okay, so I got all I can get out of that. So let me try gain. Yeah, losing them. There, now I can get some back. It's a little better. Okay. Oh, yeah, like that. Yeah. Okay, those would be my settings for today. Yeah. Okay, sorry. Toys. They shouldn't let me anywhere near them. Oh, yes, save changes. Thank you. All right. I hate Windows 10. I've already said that though, haven't I? I'll say it again just for fun. Yeah, it's pretty good eyes, right? Yeah, it's pretty cool. Yeah, it is. You even have blue teeth. Ew, ew. I gotta buy some new teeth. So anyway, where was I? Oh yeah, I was leaving. That's where I was. Yes, I'm tired. Oh. Old fan. Yeah, I was kind of, You have to let me in on the story. I mean, I don't like that you're selling your toys. That's terrible. I hope it's not for some horrific reason, like you have to move or something or do something stupid or whatever. Hope it's just like, oh, I want some space. And they're old and stupid. Yeah. Yeah, like I love the idea that you have Transformers that are all in pieces. It's funny. Well, there's 16 toys here in all different pieces. You can put all the pieces together and make stuff, but I'm not doing that. That'll take hours. All right, reference frame, double slit, probability function versus interference pattern thoughts. Well, I'm just saying there's no interference pattern, so interference is stupid. Um, the photon it's decided where the photon is going as soon as it goes into the field created by the matter, okay, that's blocking the light. So whatever you're using for a slit, whether it's even just magic marker, those atoms are creating a field of free electrons. Those free electrons move in geometric directions, and that's deciding the angle, the angle theta. Okay, that's deciding it. There's no interference anywhere. Like I said, I'm going to play with this mirror thing, but this is interesting. Because like I said, I'm getting a pretty strong, when I shine a laser on the edge of this, where you can't really see the black film now, but when I shine a laser on the edge of this black film, you really can't see it. Well, then you can sort of see it. I get the pattern just in one direction, and it's in the direction opposite to the direction I'm holding the laser, which is interesting. So the question is it getting refracted after it reflects into the mirror, or did it refract going into the mirror and then refract coming back out of the mirror? So anyway, I mean, it's interesting. So I'm going to play with that a little, and if I could find the time. But anyway, what else? I know I did something else that was interesting. I can't remember it right now, but lots of things to play with. But anyway, so there's no interference pattern. The probability function is just a function of, again, the arrangement of the atoms. Atoms have an arrangement. Oh yeah, this new camera thing is not going to work for drawings. Yeah, it's just a white piece of paper. That's funny. Yeah, it's just completely nothing. There's drawings on here. They've been diffracted away. But anyway, it's the geometry of the atoms that's deciding the probability. And there is no such thing as a reference frame. Frames are nonsense. There's an absolute reality. There's no frames. So anyway, I'll make it very soon. It's complicated. Oh dear. Little of column A, little column B. Yeah, it's never very good at taking care of, I guess, of my robots. Yeah. 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 Well. Yeah, not exactly mint condition in the box ones. Anyway, so the whole collectible thing is so crazy. Yeah, I have to go through my stamp collection sometime. Probably worth 49 cents. I have a whole big book. When I was a kid, I did collect stamps for a while. So anyway, where was I? Oh yeah, I was going. So anyway, thanks, and I'll be back when I'm back. Yeah. And such. And I guess I'll have to fix the camera if I'm going to do drawings. Damn. So yeah, until next time and such and so forth and whatnot. Oh, I should have read a comment or two, but yeah, no, they weren't that good anyway. I'll save them for next time. That's what I'll do. So, till next time. And good night. Keep physicsing. Yeah, so got an exit line, right? It's the particle, stupid. Yeah, it's, yeah, something like that. I have to find out some little catch line to insult waves. Waves be wacky, and such. Okay. Yeah. Waving be wacky. Okay. Something like that.